So the uh, next point in this unit is the virtual memory. The virtual memory is related to the internal memory of the processor. So, how is this virtual memory that we shall see in this particular topic? We have already discussed cache, but that particular cache memory is the physical memory which is present between the main memory and the CPU. Whereas virtual memory, as its name specifies, it is not physically present, it is virtual. In fact, it is there, and it is there on the secondary device like hard disk, okay, or already which is part of the hard disk. All the files or all the data or code is transferred from the secondary memory to the main memory. So as we compare between the main memory and the secondary memory, then the uh, amount of main memory available is smaller than the amount of memory available on the hard drives as the secondary memory. Okay, so you are aware that the size of the RAM is usually in GBs, whereas earlier it used to be only in MBs, that is megabytes. Now it is in gigabytes. So you have either 1 GB or 4 GB, or sometimes if you have more memory than 16 GB or 32 GB of RAM on your machine. Whereas the hard drive on the hard drive you have a lot of memory, that is nowadays it is in terabytes. So it is above, at least you have 1 TB, or even if you are having uh, older computers, then in that it was 500 GB, or it was at least above 100 GB or 100 gigabytes. So the memory which is available on the hard drive, it is large. So whenever any program is required to be executed, or whenever any file is to be operated, then it has to be brought into the main memory. For execution of the program, that particular uh, file or that particular data or that particular program has to be brought into the main memory. Then only it can be executed, or then only the operation can happen on that particular data. Uh, as the operating systems have become multitasking operating system, there are more than one programs running in the main memory. So all those programs, they have to be stored in the uh, main memory. So the amount of main memory required is very huge in such cases. Okay, so if you consider the nowadays the programs, they are also a complex program, and size required for storing one program is large, and in such cases the available main memory may not be sufficient. So if available main memory is not sufficient, then it is not possible to load multiple tasks simultaneously in the main memory. So that will be a limitation, that at a given time you will be able to run specified number of tasks. Okay, I hope you understood what is a task. That a task is something, for example, you are opening a Word file, so that is one task. Okay, so the Word program and the file opened are the files which are being transferred from the hard disk to the main memory. Simultaneously, let us say you have opened a PDF reader. So PDF reader is another program, and the file opened in the PDF reader, or more than one files may be opened in the PDF reader, and those are the data and the program for the PDF reader. Okay, so that is another task. Simultaneously, let us say you have opened some uh, uh, video file, and you are playing that particular file. So the video player and the video file for that is again another set of file required for that particular task. So like that, uh, you may go on opening the task, and your PC or your laptop allows you to open as many tasks as you need to open, and it provides the space for that is, whenever you are opening it, working with any task, then what happens, that task should be there, that task should be loaded into the main memory. Okay, so here you can see that this is the main memory, and it is divided into the various pages. Okay, and so what is this paging and what all about this we shall be discussing shortly. Uh, but I'm going to explain you the scenario that when you are opening multiple tasks, and in that case each and every program requires space in the main memory. So in such cases, what happens? In such cases, you need to provide the operating system need to provide space to all these particular tasks, and because the tasks they are complex, so that much memory may not be available uh, in your laptop or in your desktop. Okay, so in such cases, what is done is that uh, for opening the program you need memory, uh, whereas actual memory is not available. So what operating system does is that for each of the tasks it assigns the memory, and that the operating system or your processor assigns the memory to that particular task, and it is not assigned physically, it is assigned in a space called virtual memory space. Okay, so every task is assigned the memory which it requires. For example, some task requires 1 GB of memory or 500 MB of memory. It will be assigned 500 MB of memory, but it will not be assigned that 500 MB of memory in physically in the main memory space. Okay, this is the main memory space, but it will be there will be another memory space, and that is called the virtual memory space. Okay, so the virtual memory space is huge for each of the processor, and and it is automatically managed. In fact, it does not exist. Okay, because it is virtually available. So how that particular virtual memory, though it is not there, how it is managed by your processor or your operating system, so that we are going to see here, that is management of this particular virtual memory, or how virtual memory is implemented. Okay, so the idea in this case is that whenever you are loading your program, or whenever you are loading your data file or your program file, it may be very huge file. Uh, so uh, when you are loading it in the main memory, then the complete file is not loaded. Okay, the complete program is not loaded, the complete data is not loaded. Okay, for example, your PDF file, it may be of 1000 or 2000 pages. Even your Acrobat reader many MB of memory. So in that case, it will not load all the code or all the data uh, corresponding to that particular task. Okay, so every task need the data and the program or the instructions. So what is divided? The program and data of that particular task is divided into pages. The size of every page is fixed and it is 4 kilobytes. Size of every page is fixed and it is 4 kilobytes, and only the pages only the pages which are required currently from that particular task, they are loaded into the memory. Okay, for example, uh, here uh, this is the process A page table. Okay, so process A means this is the task A. Okay, so earlier this was uh, or this is the task. Okay, uh, uh, the free frame list is available here. That is frame number. That is, here you can store your pages. Okay, so page number, the frame number 13, 14, 15, 18 and 20 are the free frames. Okay, for example, this particular main memory is divided into frames. So in each of the frame, what can you store is you can store one page, and size of one page is 4 kilobytes. Size of one page is 4 kilobytes. So whenever any task is loaded, then the complete task, the complete program or complete data is not loaded into the main memory. Only few pages are loaded into the main memory. Okay, so this is your page A, and it has got, let us say, 4 pages, and in that case you can see here only 3 pages are available in the main memory. Then you need one more page from process A, and after that it has got a process A page table. So whenever that particular page is required, then that particular page is brought into the memory. So uh, the the process A has got the page list, that is page 0, page 1, page 2, page 3. So 4 pages are required. So the different pages, they may be stored in the different frames in the main memory. Again, the point to be noted here is that whenever this 4-page task is loaded into the memory, then all 4 pages may not be loaded. So here you can see that uh, memory is not allocated to this particular process A, and after this particular task has been loaded, the memory is allocated to this particular process A. And how is it allocated? So page 1 is assigned frame 18. Okay, so page 1 or page 0 is stored here at frame 18. Then uh, page 1 is stored at this particular frame 13. Then page 2 is stored at uh, frame 14, and page 3 is stored at frame number 15. Okay, so like this, the 4 pages corresponding to this particular process A are loaded into the memory. Okay, so here we have shown that this is the page table, and this particular page table contains where which particular memory or which particular frame is assigned to a particular page. So 4 pages are there. So all the 4 pages have been allocated 4 frames, and this particular assignment is done in the page table. Okay. Now here we have shown that the all the 4 pages have been assigned 4 pages in the main memory, but in fact it will not happen always, and only the required number of pages will be allocated memory. Okay, So here there may be many pages, let us say 10, 15 pages here, but only 2 to 3 pages of that particular task will be assigned the frames. For example, this particular slot is always for page 0, page 1, page 2, page 3, and like that. Okay. So some of the entries in this particular page table may be empty. Some of the entries in this particular page table may be empty. So what does it mean? The entries are empty. It means that that particular page is not loaded into the memory. So whenever that particular page is required, then in that case, that particular entry will be filled, and then the processor will access that particular page. Okay. So if there are, let us say, 100 pages for process A, let us say there are 100 pages for process A, so page number 0 to page number 99, then there will be 100 locations in this particular page table. Okay, so location 0 or entry, there will be 100 entries, you can say, in this particular page table. Okay, so entry 0, 1, 2, 3, 4 up to 99. Okay, but out of this 100 entries, only few entries are filled. That means only few pages are loaded into the main memory, whereas the other pages are not loaded into the main memory. They are loaded into the main memory as and when they are required. But the feel is given to the processor that all the pages, all 99, all 100 pages are loaded into the memory. Okay, so the actual size required for loading this particular program is 100 multiplied by 4 kilobyte. The size of each page is 4 kilobyte. So the total size of the process A or the task A is 100 multiplied by 4 kilobyte, that is 400 kilobytes. So if we would have loaded this particular program into the main memory, then 400 kilobytes of main memory would have been required. Okay, but we are loading only, let us say, only 4 pages. So 4 pages would require 4 into 4 kilobytes, that is only 16 kilobytes of memory is required. Okay, so when, but it may happen that your program is executing, so at some time you need one page, at the other time you need some other page, and in that case what may happen? In that case, when some new page is required, then at that time the old page may be removed from this particular main memory. For example, this page, the CPU was working with page 1 of process A. Then after some time, this page 1 may be removed, and at that place, the page number 15, let us say, may be placed. Okay, so that is at frame number 13. Okay, so here frame number 13 is now allocated to page to page 1. Okay, so after page number 15 is required, the in that case what will happen? This particular slot in the page table will be made empty, and the location for in the location for the in the entry for the page number 15, the frame number 13 would be written, so that this particular frame, which was earlier used for storing page 1, now it will be used for storing page number 15. Okay, so like this, the unrequired pages, they are removed from the main memory, and the required pages are brought into the memory. So this is how the virtual memory is implemented. Okay, so the process feel that it has been allocated 400 kilobytes of memory, but in fact it is not actually allocated 400 kilobytes of memory. It is allocated virtually in the page table, because entries there are as many as 100 entries in this particular page table, but the in physical memory is allocated only to 3 4 pages, and just 16 kilobytes of physical memory is allocated to that particular task. Okay, so we say that the memory allocated to that particular task is the virtual memory. Okay, so this is how it is allocated. Now you can see here that when we are talking about the virtual memory, then one of the important thing is that you need to do the address translation. Okay, so you need to translate the logical address to the physical address. Okay, so whenever you are working with the programs, then it is the logical address, and in the instructions. For example, on the page one, the uh, the word number 30 is to be read from the page number 1. Now it is expected, your program is expecting that the pages are stored sequentially, that is page number 1, page number 2, page number 3, page number 4, that is all instructions, they are in sequential nature. But actually these instructions, they are not in the sequential nature. So in that case, that is why what is required, whenever you are allocating uh, s- uh, 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 the space in the virtual memory, you need to go for translation of the virtual address, or it is also called the logical address, to the physical address. Okay, so this is the logical address, that is this is the page number. So this particular page number belongs to the number which is there in the virtual space. This is the virtual space. This is page 0, page 1, page 2, page 3, like that. Okay, so it is page number 1 and the location 30 in the page number. So this is to be read. So in that case, before actually this particular location is read, it goes through this particular page table. Okay, so this address CPU goes to this particular page table. So it goes to the page table where the translation of the address happens. So page number 1 is allocated frame number 13. So here this one, page number 1, is replaced with the frame number. So it is frame number 30, and then in the frame number 30, the 30th location will be accessed. So it goes in the main memory to the page number 13, and it accesses that 30th, 30th location. Okay, so this is how the translation occurs before anything is read from the main memory. So this particular translation is called logical to physical address conversion, or virtual address to the physical address conversion. Okay, so this is specified in the other way here. Okay, so this is you have the virtual address. In the virtual address consists of the offset and the page number. The page number is specified using certain number of bits, and offset is specified using certain number of bits. Okay, so this particular page number is obtained, and it goes through some hash function, and these n bits are converted to m bits, and here this is the page table, and you go to that particular page table to search the location, to search the location of this particular page, the entry which is stored in this particular page table, and that is called the page entry. So in the page entry, you have again, so there can be such that in the page table you may not directly get the frame number of that particular page. The entries may be such that you will be getting the entry in the page table, and that particular entry will not be directly giving the frame number. It may be giving the reference of the another entry. For example, here you have this particular entry. Your virtual address is specifying some entry in the page table. So that particular entry is specifying that your frame number will be available at some another entry. So with that another entry, that is I. So you go to the ith location in the page table, and in that particular page table, uh, 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 so you go to that particular location, and from that particular location you will get the actual frame number or frame address, and that particular frame address will be used. The offset in that particular page will be same, and that will be the real address or the physical address. So this is how the virtual address is converted to the physical address or real address, and that happens through a table, and that particular table is called the page table. Okay, so this is called the paging mechanism. So in all the advanced processors, this particular paging mechanism exists, and this particular paging mechanism implements the virtual memory. So that is how the virtual memory is available. Now this is the uh, Uh, this is the uh, another diagram which shows the conversion of the uh, conversion of the virtual address from the processor to the physical address in the main memory. Few more details have been shown here in this. uh, with the processor like the 80386, which is the predecessor of the Pentium processor, you have a special register for this particular paging, and that particular register is called page table base register. Okay, so your address of the memory location is in this fashion: virtual page number and offset. So this with this particular virtual page number, uh, the processor uh, goes to the page table. Now this, where is this particular page table? The page table again is there in the memory. So Uh, the location of the page table in the memory is specified by a register which is there in the CPU or which is there in the processor, and that particular register is called page table base register. So it contains the address of the page table. Okay, so the address of the page table is available in the uh, page table base register. Okay, so to that address, you need to add something based on the virtual page number, because the entries are sequential in fashion. So if this particular page number, virtual page number is 0, then your entry is in the beginning of this particular page table. If it is let us say maximum, then your entry is at the end of the page table. Okay, so this particular virtual page number, it varies from minimum, that is 0, to maximum, and depending on that you go to a particular entry in this particular page table, whereas the starting of this particular page table is is specified by this particular page table base register. Okay, so by adding the appropriate number into the page table base register or this particular address, you go to the appropriate entry in the page table. Once you go to that particular entry, then at that particular entry, the actual page frame address is present. So that particular actual page frame address is loaded into the page frame. Okay, and then this virtual address is converted to the physical address. Okay, but the point here to be noted that always whenever you are going into this particular page table, you may not get the address of the page frame. Okay, for example, all the entries in this particular page table, they are not filled. The the entries are not filled. Only few of the entries in the page table are filled, while the other entries are not filled. So if what happens if the entry is, some entry is not filled, some entry in the page table not filled, it means that the page is not actually present in the memory. So the page, when the page is not present in the memory, then in that case the page need to be brought into the memory. So from where the page is brought into the memory, it is brought into the memory from the secondary storage. That is all the pages, they are there on the secondary memory, that is hard drive. And from that particular secondary memory, it is brought into the main memory. So it will be allocated some frame in the main memory, and address of that particular frame in the main memory is put into the required entry, and uh, then that particular virtual address will be converted to the physical address. That means whenever some entry which is referred in the page table is empty or it is blank, then uh, that particular situation is called page fault. Okay, so it is called page fault. And when page fault occurs, whenever page fault occur, then what happens, the page is required to be brought into the main memory. Okay, so sometimes you may be feeling that whenever you are trying some different operation with the software, then your software does not immediately respond. So what is happening at that time, you are looking, or you have started some different feature of that particular program, and the instruction corresponding to that particular feature isn't available in the pages loaded in the internal memory. And that particular those particular pages are are have been allocated virtual memory. That means actual entry is not there, and in that case there is a page fault. And whenever there is a page fault, then execution of your program halts there. Okay, or it does not halts, in fact it suspends. And then there is another program in the operating system which comes into the picture when there is a page fault. So whenever there is a page fault, the the faulting page which is not present in the memory is brought into the memory from the secondary device. And after it is brought into the memory, the appropriate entry in the page table is filled, and then the program resumes again. So when the program resumes again, then it finds that the required page is present in the memory, and it continues with that particular execution of that particular instruction. So this is how you may experience sometimes a delay while executing some program. Okay, so this is the translation. So most important part in the uh, you can say virtual memory is conversion of this particular virtual address to the physical address. So in the different literature it has been shown in a different fashion. This is the way the conversion of virtual address to physical address is shown in the book of Hamacher Jackie, whereas this is the way the conversion of virtual address to the real address is shown in the book of Stearns. So it is the concept is one at the same, only the representation is different in this particular conversions. Okay. Now, again, this diagram is showing two levels of paging. Uh, so usually in the Pentium processors, they have two levels of paging. So in that case, your virtual, this is the virtual address or the logical address. So in that case, your virtual address or logical address is divided into three fields. So this is the offset, you can say. Uh, then this is the page number, and this is the page table number. Okay, so the three fields in the virtual address. Uh, this is the offset, that is the page. Uh, you can see here PD. It has been shown here. uh, the destination page, the offset in the destination page. Okay, so how much your location, this is the part of the main memory. Okay, and this location is to be accessed. Okay, so it is there at this particular offset away from the start of the page. So the first, you can say, this particular 12 bits they give that particular address. Okay, offset address. The middle 10 bits they give the page number. Okay, and the uppermost 10 bits they give the page table number. Okay, then here the page table register, the page table register, that which we have already discussed, that is uh, you also call it as the page base address register, which contains the address of the page table. Okay, so actually this is not the page table, it is called a page directory. Okay, so you can see here that it has been labeled that page table directory. So this is the first level of the page table. So there are 1024 entries in this particular page directory. Okay, so this particular implementation of paging is quite standardized. That is, in all the processors, it is used in the similar fashion. So size of every uh, you can say frame or every table, it is 1 kilobyte. Okay, so this is 1024 entries here, 0 to 1023, that is 1K entries, and size of each entry is 4 bytes. So size of this particular page directory is 4 kilobyte. Okay, so in the paging mechanism, the size of the page table directory is 4 kilobyte. Then at the second level you have page tables. Okay, so you have so many page tables in the in this particular virtual memory implementation. Okay, so this is the 0th number page table, this is the first page table, second page table. So how many page tables you can have? You can have up to 1024 page table, that is 1K page tables. Okay, so one page directory, 1024 page tables. And then in each of the page table, each entry in the page table may refer to the pages. Okay, for example, only one entry has been shown here, and it refers to a page in the main memory. Okay, so you can see here that uh, the paging is implemented using two levels. That is, you have the page directory, then you have the page table, and then you have the actual pages in the internal memory. Okay, so this is two level of paging. So how it happens? uh, uh, from this particular virtual address, first of all, upper 10 bits are used to locate the page table. Okay, so this particular bit will select one of the entry in the page directory. So each of the entry in the page directory will give you the address or the location of a particular page table. Okay, so one of the entry will be selected, so that will give you the page table address. So here we get the address of the page table. Okay, so depending on this particular entry, so from this particular page table entry, we go to that particular page. Okay, so again that particular page has got 1024 entries, and each of the entry is going to specify the the address of a particular page. Okay, so in the page table, you can say, this is the entry. So this particular page number. So after you have located the page table, then in that particular page table, a particular entry will be selected by the second field, that is so in this 1024 entries are there, so a particular entry will be selected by this particular page number, and this particular entry contains the actual address of the page, and that with that particular address you go to the start of that particular page, and from the start of the page, then the third field give you the actual location of the memory to be accessed. Okay, so it will be either read or it will be written. Okay, so this is how the memory is read. So directly this is the address which is given in the program, but this address is not used. This address is converted from the physical address to the sorry, this address is converted from virtual address to the physical address. Okay, so again this is the address conversion using the two level page table, which is actually used in the processors like the Pentium processors. Okay, now this is the page table. Okay, that is a page directory and the page table for one task. Okay, so for every task like this, the different page directory and page tables are existing. Okay, so how many pages can be there in one task? So that depends on how many entries are available in this particular page table. So there can be as many as 1K page tables. Okay, and in each of the page table there are 1024 entries. So 1024 into 1024, so the total entries, it may be 1 mega pages. So 1 mega pages entry is there, and for uh, and size of each page is 4 kilobytes. So 4 kilobytes. So how much virtual memory is allocated to one task? It is 4 GB of memory that is allocated to one task. Okay, but actually the actual internal memory available with the processor, it may be just 1 GB, but uh, virtually that particular task is allocated 4 GB of memory. Okay, so this is for one task. Then let us say your processor is switching from one task to the another task. So all these tables, they remain in the memory. So these are the tables and the page directory for one task. So they remain in the memory. Then similar page directory and similar page tables are there for the another task. And when CPU is working with the another task, then what it does is that it just changes the address of the page table register. Okay, so page table register, it was containing the base address, or it was containing the address of this page table directory. Now when it is switching to another task, then another page table directory is there, and the contents of page table register will be uh, modified so that it contains the page table directory address of that particular task. Okay, so like this, the page table directory and the page table, they exist for each of the tasks. That means every task can be allocated 4 GB of memory, and you can have as many tasks as you need in the uh, memory. Okay, so this is how the processor feels that all the tasks are there in the memory, and it has every task is allocated 4 GB of memory. Okay, this is how is the sequence of operation that happens when the CPU is going to uh, convert the address from the uh, logical address to the physical address. Okay, now here in the earlier diagram we have not explained uh, the TLB, that is translation look aside buffer. Okay, so every time it does not go through the page directory and page table to find out the actual address of the memory, but it does that through so-called TLB, that is translation look aside buffer. Okay, so otherwise what happens if for accessing every memory location in the internal memory, if it goes to through this particular, first it need to read this page table. From page table it need to go to the one of the page table. From page table it need to read the entry, and then it will go to the particular page, and then it will read that particular page. That means before reading any reading or writing or accessing any location in the main memory, it has to go through two reads. That means to read one location, two extra reads are to be done from the main memory. So what happens? Your execution of your program may slow in this case if every time your processor is going to the page directory and page table to get the address of the location to be read from the internal memory. Okay, so in that case, this particular TLB is used. TLB stores the addresses of recently uh, visited pages, and it is stored in the cache inside the processor. So if some page is already is visited, then its address, that is its physical address, is stored into the cache. Okay, so that the same thing has been explained here. So we shall see here diagrammatically how it happens. So this is the TLB, this is the virtual address. Okay, this is the virtual address. So this is the virtual page number, and this is the offset. Okay, so uh, the what the processor does is that in the normal case, means what we have explained is that this particular, with this particular virtual page address, it has to go to the page table. So page table gives you the conversion from the virtual page number to the physical page number, and to that particular physical page number the offset is added, and uh, and uh, that particular memory uh, is you can say referred. Okay, again you have the cache, and already we have discussed what happens in the cache. So if the cache is there, then it you need to if it is present in the cache, then it will be read from the cache. Otherwise there will be cache miss, and then this particular main memory will be accessed. Okay, so keeping aside the cache operation, because we have already discussed it, how the cache operates in the last unit last topic. Okay, so here you get the physical address. Okay, but you need to go through this particular page table, okay, to convert the virtual address to the physical address. Okay, but if the page is already visited, then that particular conversion, that is virtual address to the physical address conversion, is stored in this particular table that is called the TLB, that is translation look aside buffer. So before CPU go for this particular page table, which is outside the CPU, it go to a cache which is inside the CPU, and in that particular CPU it contains the virtual address physical address combinations of last visited pages. So if that exists, if the some page was last visited, then it gets the physical address. It gets the physical address of that particular page from the translation look aside table itself, to translation look aside buffer itself. So it does not need to go it does not need to go to the page table. Okay, so here you can say that it will be a TLB hit. Okay, so if the page is already visited, or that particular page was already referred, then you do not need to go to the page table to find out what is its physical address. So you get it from the TLB itself, so it will be TLB hit. But if it is not there, then in that case it will be TLB miss, and in that case it will go to the page table, and that particular physical address is found from the page table, and then that particular location is accessed. But while doing so, that entry new table sorry new page entry is added in this particular TLB, that is translation look aside buffer. Okay. So this is all about the translation look aside buffer and virtual memory. This is uh, shown in the another fashion, and how the TLB operates. Okay, so this is the virtual page number. So this particular virtual page number is compared with this is the required virtual page number. It is compared with the entries in the TLB. If the match is there, then there will be hit. So the page frame number will be taken from the TLB. Otherwise, whenever there is a miss, then in that case it will be taken from the page table. Okay, so this is how is the TLB functions and the operation of the virtual memory. So I hope you have understood this particular concept of virtual memory. Any doubt in this?
Sir, sometimes I mean I've seen some YouTube videos where it is showed